Okay, so the reactive and etching, there are two types of generators. One is called ICP, which is ICP chamber, which is inductive coupled plasma. Another is capacitive coupled chamber, which is generated by the sample sets. Uh, so now, what is the role of frequency? Normally, if you see the RF1 is set at 13.56 megahertz and ICP1 is set at 2 megahertz. What is the reason behind this? Basically, the 13.56 megahertz and 2 megahertz is the industry standard, while 13.56 megahertz is more common for the plasma. Why did they choose this number? I mean, many manufacturers I have seen using 2 megahertz for both of the RF generators, 13.56 for both of the generators, even 100 kilohertz for RF generator, which is the lower chamber, which is also called the lower chamber. But what is the reason behind it? The reason is very simple. If you look at this graph, this is the silicon etch rate. Which in this side, this is the x-axis is the frequency, and this is the bias developed process sample, which is normally your the peak to peak voltage developed process sample. So if you see at 2 megahertz or 1 megahertz, it's, the peak to peak voltage starts dropping. So the idea is the lower frequency you have, the more energetic, the more concentrated number of neutral and ions are going to the sample. They are not distributed, they are not spread out, they are focused at one energy. So overall, you get more energetic ions. In this case, if you see the silicon etch rate also decreases. So these people have to come with some numbers to get your etching rate maximized, as well as you don't want to kill your selectivity. So, for example, the system which I have seen recently by Oxford and Exantec, they use 2 megahertz for ICP and 13.56 megahertz for RF, your bottom electrode. So now one of the, again, interesting question is why there are some plasma hard to strike. For example, take the example of CCl4 or SF6 most probably. The reason is these plasmas are electronegative in nature, while argon and nitrogen are electropositive in nature. Remember that you need electrons to sustain the plasma. In case of electronegative plasma, the negative ions take their place, and they are very harder to accelerate compared to electrons, and in other ways, you don't get your plasma stable. So you need to, that's why you will be saying that you need to add argon or nitrogen in these electronegative plasmas. There is a in between this electropositive and negative plasma, there is some gases which falls in intermediate range, which is also good to stabilize the plasma or some other reasons. For example, O2 and hydrogens. So here is their order of electronegativity going from left to right. Now, if you see the number of electrons with energy, so if you see the number of electrons in electropositive plasma, it's quite high, although they have a less energy. Electronegative plasma, the number of electrons are quite less, so which makes it difficult to sustain the plasma. Second from this, one of the most, again, important effect is the loading effect. What happens if you put two, because you want to achieve as much as you can, so you want to achieve maybe 10 wafers, so 4-inch, is it possible? Will it give me the same results? The reason is no. Yeah, I mean, so the answer is no. The reason being that you have a limited amount of neutral and ions with the same, keeping the same condition. Let's say you keep the power, pressure, temperature, everything constant. So you're going to consume more of these, and apparently at some point of time you'll have a more material to etch than your neutral ions can support. So eventually you're going to have a decrease in etch rate. So here is saying they're plotting 1 by etch rate. So this means this has a lowest etch rate. So higher number wafer, it has a lowest etch rate compared to the, let's say, 1 wafer, or compared to 1 wafer, yes. So it decreases by almost half, from 3 to 6 wafer. Now, this is the slide which most of us should be knowing. Why? I mean, I was wondering why there's sometimes hydrogen being used, why there's sometimes oxygen being used. in addition to the gases, which is normally, for example, take silicon, right? You want to etch it with chlorine, but why are you adding something else? So you take silicon oxide, you can etch with chlorine, but why are you adding something else? Uh, it was uh, I was not, I mean, not understanding at that point, but now I realize there is a reason for that. For example, take oxide etchant. So additive here is an oxide etchant. So you want to etch silicon oxide, basically you can etch with chlorine. So, but this material you use C2F6 to break through their oxide because silicon form a silicon oxide. So you break through silicon oxide. Uh, Same example with aluminum oxide. You use BCl3 to break oxide, and then you etch your material in the resin cells. So another one is oxidant. So you add oxygen. So this decreases this suppresses the polymer formation due to fluorocarbons. As I already told you, inert gas nitrogen is as argon or helium being used to stabilize the plasma. And then, for example, in Boss process, you need to form polymers. For example, uh, improve selectivity, induce selectivity. So silicon being used actually with chlorine, but C2F6 as C2F6 has been used to polymer formation on the walls. In some reactions, you will have to use a radical sponger, which will eat your radicals because you'll have a too high H rate. For example, hydrogen will act as one. Um, then we'll have a volatile laser. So you want to, burn the oxides with the form a volatile product with oxygen so that you can have a more H rate. So this is a very important slide. So the way you have to read is from right to left. So the material you are going to etch is silicon oxide. Etchant gas is chlorine. What are you adding? This is additive. So there is a way to read it. Now, one of the question coming to will be your mind if you are etching it using RIE every day. What is chamber made of? I mean, how come the chamber is not being eaten up? Chamber is being eaten up, although it is very, very slow. So you should know when you are using, let's say, fluorine chemistry, how much it will affect your walls. Let's say I use boron nitride or zinc or brass. If you see your loss probability, I mean, how much fluorine will be you can say kind of uh, reaction will be happening. Boron nitride is worse for this fluorine atoms. Um, it will almost, there is almost a probability that it will be, it will form a reaction with this chamber. On the other hand, if you use alumina quartz, the reaction probability, the loss probability is very, very less, which will give you the longer lifetime of the chamber. That's all from